Okay, so this little mini unit is about color.
One of the most striking properties about light is that it has color. To understand the phenomenon of color, it helps to think about light as a wave. But before we get to that, let's talk a little bit about waves in general. Imagine you're sitting on a boat on the ocean, watching a cork bob up and down in the water. The first thing you notice about the motion is that it repeats itself. The cork traces the same path over and over again, up and down, up and down. This repetitive or periodic motion is characteristic of waves. Then you notice something else. Using a stopwatch, you measure the time it takes for the piece of cork to go from its highest position down to its lowest and then back up again. Suppose this takes 2 seconds. To use the physics jargon, you've measured the period of the waves that the cork is bobbing on. That is, how long it takes a wave to go through its full range of motion once. The same information can be expressed in a different way by calculating the wave's frequency. Frequency, as the name suggests, tells you how frequent the waves are. That is, how many of them go by in 1 second. If you know how many seconds one full wave takes, then it's easy to work out how many waves go by in 1 second. In this case, since each wave takes 2 seconds, the frequency is 0.5 waves per second. So, enough about bobbing corks. What about light and color? If light is a wave, then it must have a frequency, right? Well, yes it does, and it turns out that we already have a name for the frequency of the light that our eyes detect. It's called color. That's right, color is nothing more than a measure of how quickly the light waves are waving. If our eyes were quick enough, we might be able to observe this periodic motion directly, like we can with the cork in the ocean. But the frequency of the light we see is so high, it waves up and down over 400 million times a second, that we can't possibly see it as a wave. But we can tell, by looking at its color, what its frequency is. The lowest frequency light that we can see is red, and the highest frequency is purple. In between, all the other frequencies form a continuous band of color called the visible spectrum. So, what if you had a yellow pencil sitting on your desk? Well, the sun emits all colors of light, so light of all colors is hitting your pencil. The pencil looks yellow because it reflects yellow light more than it reflects the other colors. What happens to the blue, purple, and red light? They get absorbed, and the energy they're carrying gets turned into heat. It's similar with objects of other colors. Blue things reflect blue light, red things reflect red light, and so on. White objects reflect all colors of light, while black things do exactly the opposite, and absorb at all frequencies. This, by the way, is why it's uncomfortable to wear your favorite Metallica t-shirt on a sunny day. You might have heard that light is a kind of wave, and that the color of an object is related to the frequency of light waves it reflects. High-frequency light waves look violet, low-frequency light waves look red, and in-between frequencies look yellow, green, orange, and so on. You might call this idea physical color, because it says that color is a physical property of light itself. It's not dependent on human perception. And while this isn't wrong, it isn't quite the whole story either. For instance, you might have seen this picture before. As you can see, the region where the red and green lights overlap is yellow. When you think about it, this is pretty weird. Because light is a wave, two different frequencies shouldn't interact with each other at all. They should just coexist, like singers singing in harmony. So, in this yellow-looking region, two different kinds of light waves are present. One with a red frequency, and one with a green frequency. There's no yellow light present at all. So, how come this region, where the red and green lights mix, looks yellow to us? To understand this, you have to understand a little bit about biology, in particular, about how humans see color. Light perception happens in a paper-thin layer of cells, called the retina, that covers the back of your eyeball. In the retina, there are two different types of light-detecting cells, rods and cones. The rods are used for seeing in low light conditions, and there's only one kind of those. The cones, however, are a different story. There are 3 kinds of cone cells that roughly correspond to the colors red, green, and blue. When you see a color, each cone sends its own distinct signal to your brain. For example, suppose that yellow light, that is, real yellow light with a yellow frequency, is shining on your eye. You don't have a cone specifically for detecting yellow, but yellow is kind of close to green and also kind of close to red, so both the red and green cones get activated, and each sends a signal to your brain saying so. Of course, there's another way to activate the red cones and the green cones simultaneously, if both red light and green light are present at the same time. The point is, your brain receives the same signal regardless of whether you see light that has the yellow frequency or light that is a mixture of the green and red frequencies. That's why, for light, red plus green equals yellow. And how come you can't detect colors when it's dark? Well, the rod cells in your retina take over in low light conditions. You only have one kind of rod cell, and so there's only one type of signal that can get sent to your brain, light or no light. Having only one kind of light detector doesn't leave any room for seeing color. There are infinitely many different physical colors, but because we only have 3 kinds of cones, the brain can be tricked into thinking it's seeing any color by carefully adding together the right combination of just 3 colors, red, green, and blue. This property of human vision is really useful in the real world. For example, TV manufacturing. Instead of having to put infinitely many colors in your TV set to simulate the real world, TV manufacturers only have to put 3, red, green, and blue, which is lucky for them, really.
Color is not an inherent quality of objects in the world. Color is a construct. Color is an illusion created between your brain interacting with the properties of luminescence, reflectivity, and shadow. Think about the takeaway of that idea. We can only know the world through the signals that are perceived through our instruments that we call the senses. Our consciousness sits in our brain, which sits behind 2 inches of skull. Our eyes are not windows from which our brain sees the world. The world is constructed for you by your brain, using the limited information that it can receive through the senses. The rest is fill in the blank. It's a theater that we put on for ourselves. We can never know the world directly. All we can know is a representation, a rendering, a cosmic dance between our brain and those signals coming in. And our brain is throwing in intention, expectations, preconceptions, stereotypes. All of these things are also informing what we perceive. You start with this idea that color doesn't exist. You end with the idea that nothing really can be known directly, so that everything is itself a rendering or a simulation.
So this is the one about the combining of the senses, the one I put in because it's really interesting.
Imagine a world in which you see numbers and letters as colored, even though they're printed in black, in which music or voices trigger a swirl of moving colored shapes, in which words and names fill your mouth with unusual flavors. Jail tastes like cold, hard bacon, while Derek tastes like earwax. Welcome to synesthesia, the neurological phenomenon that couples 2 or more senses in 4% of the population. A synesthete might not only hear my voice, but also see it, taste it, or feel it as a physical touch. Sharing the same root with anesthesia, meaning no sensation, synesthesia means joined sensation. Having one type, such as colored hearing, gives you a 50% chance of having a second, third, or fourth type. 1 in 90 among us experience graphemes, the written elements of language like letters, numerals, and punctuation marks, as saturated with color. Some even have gender or personality. For Gail, 3 is athletic and sporty. 9 is a vain, elitist girl. By contrast, the sound units of language, or phonemes, trigger synesthetic tastes. For James, college tastes like sausage, as does message and similar words with the "age" ending. Synesthesia is a trait, like having blue eyes, rather than a disorder, because there's nothing wrong. In fact, all the extra hooks endow synesthetes with superior memories. For example, A girl runs into someone she met long ago. Let's see, she had a green name. Deezer Green. Deborah, Darby, Dorothy, Denise. Yes, her name is Denise. Once established in childhood, pairings remain fixed for life. Synesthetes inherit a biological propensity for hyperconnecting brain neurons, but then must be exposed to cultural artifacts such as calendars, food names, and alphabets. The amazing thing is that a single nucleotide change in the sequence of one's DNA alters perception. In this way, synesthesia provides a path to understanding subjective differences, how two people can see the same thing differently. Take Sean, who prefers blue-tasting foods such as milk, oranges, and spinach. The gene heightens normally occurring connections between the taste area in his frontal lobe and the color area further back. But suppose in someone else that the gene acted in non-sensory areas. You'd then have the ability to link seemingly unrelated things, which is the definition of metaphor, seeing the similar in the dissimilar. Not surprisingly, synesthesia is more common in artists who excel at making metaphors, like novelist Vladimir Nabokov, painter David Hockney, and composers Billy Joel and Lady Gaga. But why do the rest of us non-synesthetes understand metaphors like sharp cheese or sweet person? It so happens that sight, sound, and movement already map to one another so closely that even bad ventriloquists convince us that the dummy is talking. Movies likewise convince us that the sound is coming from the actors' mouths rather than surrounding speakers. So, inwardly, we're all synesthetes, outwardly unaware of the perceptual couplings happening all the time. Crosstalk in the brain is the rule, not the exception. And that sounds like a sweet deal to me.
So I've never met anybody that has that. Do any of you guys have that? Has anyone ever met anyone who says that? Has said that to you? Seems really odd, doesn't it? It's hard to imagine. Okay, so color mixing, there's two types. Additive. Held together with it would be an with additive color, we're dealing with the colors red, green, and blue. And they mix together to form all the other colors. Notice from the earlier film that they are exactly mirroring the cones in your eyes, right? Those are the only cones we have. We don't have a cone for yellow. We don't have a cone for orange, but they can mix together. If you look at the little diagram, you can kind of see what happens. So where the blue and green spotlights overlap, you see cyan, which is that light blue. Where blue and red spotlights overlap, you see magenta, that hot pink. Where red and green spotlights overlap, the color yellow is produced. That's the odd one to me, that a light yellow can be, produced with green and red. And then finally, if you mix them all together, you get pure white light. So in your monitor, in your TV, on the stage, that's all dealing with the additive color mixing method. Subtractive color is the process of mixing inks, paints, or dyes. Colors subtract a portion of the spectrum of white light that is illuminating an object. The color of an object is a result of the color lights that are not absorbed by the object. So here we have the traditional color wheel on the left and the printing, or also called the CMYK color wheel. This is also referred to as process color. And notice that the red is subbed out for magenta, and that wheel just happens to be backwards because you can flip them. But, so flip it. The blue is the cyan, and the yellow stays the same. So with not just the traditional color wheel, but with all color wheels, there's a system that's involved in terms of how they're laid out. And it isn't, color wheels are not just pretty wheels that have all the colors of the rainbow. They're actually a system about the way things that are organized. So if you look in the middle and you see that big middle triangle, that is the primary triad, the blue, yellow, and red. And those colors make all the other colors. So if you were a starving student and you needed to paint and you wanted to paint with more than just 3 colors, if you bought those colors, then you could make all the other colors. Now the next group of colors going out from that triangle are the green, orange, and purple or violet. Those are the secondary colors. They're created by the mixing of the primary. So when you mix your blue and yellow, you get your green. When you mix your yellow and your red, you get your orange. When you mix your red and your blue, you get your violet. The colors going around the outside reflects both the primary and the secondary. So you can notice there's the blue of the primary, the yellow, and the red. And then there's also the green, violet, and orange. There's an additional 6 colors, and those are the tertiary colors. Those colors are created when you mix a primary with a secondary. So, for example, mixing our yellow primary with our green secondary gives us yellow-green. Mixing our red primary with our orange secondary gives us red-orange. And I'm going to pause that just because I like to point that. I want to point that out. I didn't want to leave. Usually I come over here and point it out, but since I was recording, I wanted my voice to touch. So you can kind of see the one people get confused about is the tertiary colors, and those are the 6. So here we have primary, mix, secondary, and then if we take a primary and mix it into a secondary, we get the tertiary. So it's right here. So it's not here. This is the blue. It's there. Between violet and blue, blue-violet. Between violet and red, red-violet. And those color names, the true names, are just the combo of the two, of the primary with the secondary. Although we often give them more descriptive names like lime green, but really that's yellow-green on the wheel. So just keep in mind the wheel is not just a pretty, thing for color. It's not just a pretty wheel full of color. It's actually a tool that artists and designers use to mix color. It's also a tool that artists and designers use to come up with color schemes. And we're going to make color wheels first, and then we're going to start working with color schemes. I'm going to show you, though, actually, the mixing of the subtractive wheel too, or excuse me, the additive wheel, and then I think after that it'll stop. So let's see, we want shift 2. Might need to escape right now. And then play.
Oh, there are 3 primary colors. Only 3 are primary, it's true. The world is full of every kind of color, but we're just talking red, yellow, and blue. Red, yellow, yellow, blue, blue. These 3 are the primaries, it's true. Oh, there are 3 primary colors. Only 3 are primary, it's true. But if you mix the primaries together, brand new colors come right into view. Red and yellow make orange, red and yellow make orange, yellow and blue make green, yellow Yellow and blue make green. Blue and red make purple. Blue and red make purple. And that's a lot of colors to be seen. There are 3 primary colors. And lots of other colors out there too. But when you see any other color, they're all made up of red, yellow, and blue. Red and yellow make what? Red and yellow make what? Yellow and blue make what? Yellow and blue make red. That's right. Blue and red make what? Blue and red make what? That's a lot of colors to be seen.
Okay, so here's the CMYK wheel, and it's really the same as the traditional wheel, pretty much in the way that it mixes, although the colors are different. In that, you know, instead of the dark blue for the primary, you're using the cyan, and instead of the red, you're using the magenta. So this is the color system that is in the cartridges in your printer. The C, cyan, the M, magenta, the Y, yellow, and then who knows why they chose this, but K represents black. Yes?
Because if they use B, they might mistake it for blue.
That's probably why. You're right. Okay, here's how it mixes. So if you take a file that you make in Photoshop or Illustrator and you send it to the printer and they're going to print it, unless they're using color Xerox, they're going to use a lithographic process, which involves using plates. And what they'll do when they get the work, and usually anything like a magazine, a poster, a newspaper, you know, they're all going to be printed with a lithographic press because that's kind of a more clear, clean press. Magazines too, as well. So they'll color separate your file, and then they'll make 4 different plates. One for the cyan, one for the magenta, one for the yellow, and one for the black. They'll run the paper through the printer 4 times to create full color. And so it's quite an involved process to end up with the full color image. Now, if you have a client that wants to save money, say they have a very limited budget, then what you want to do is limit the color, and then it doesn't have to run through the press as much. So if you look over on the wall over here this way, which would be the south wall, notice the orangey red and the green or the bluish posters. Those are all one color. The white doesn't count. That's the white of the paper. So that particular series of posters was way cheaper to print. Didn't have to go through the press 4 times. And imagine they were printing 50,000 of them. So you see, it would really save a whole lot of money. Now, the way that the little plates work, they have little dots on them, and the dots are at different angles. And so as they get, you know, they're basically, usually they start with yellow, and then they do, I don't remember which one's next. I think black is last. But they run through, and it kind of places that color in a way that it's going to show the full color. If you look at that left image at the top, to the right of it, you see the close-up of what that image would look like. So it's a bunch of pure color, you know, that is the CMYK mixing together to create the color. And then looking at the halftone dots, notice that in relation to that gradient that's to the right of it, that the dots are closer together when you see darker, and then they get farther apart with more space in between when they're showing lighter. Now, spot colors are also an option, and it's possible that those posters were a spot color because, you know, what you'd want to do is pick a definite color exactly, you know, you can get the exact ink. They're often used for one-color jobs, and then also if you have a specialty ink that you want. Maybe you want fluorescent ink, or you want silver or gold or copper, a metallic. That would be a spot color. Pantone color is the color system for spot colors that we mostly use in the United States. It's the most dominant color system. And they have a whole series of little swatch books So say you were doing a one color poster, you would go down to the print shop and you'd use the swatch book to pick out the exact color that you wanted. That's going to be more accurate than your monitor, the color on your monitor. So RGB relates to television screens, computer monitors, and also the cones in our eyes, the red, green, blue color system. And here's the additive color wheel. Notice it has the triangles. It has the primary triad, it has the secondary triad, and then it has the intermediate colors, otherwise called the tertiary. Those are the ones that are made mixing, for example, the red primary with the yellow secondary to get the orange intermediate tertiary color. Tertiary for third.
You wake up in the morning, you look in the mirror, and you decide how you look or how you feel. Most
I'm going to stop there actually.